Okay, let's do another example. This time we've got the window company. For this one, go ahead and try to pause the video, try to work through the problem, formulate the linear program, then go ahead and graph it using Desmos or by hand. Find those corner points, figure out what is the objective value at each of those corner points, and then solve it. And then we've got some follow-up questions here at the bottom. Give those a try. They're a little bit more challenging. A couple of what ifs. What happens if we change a couple things? What happens if we change the profit margin? What happens if we change Jacob's labor hours? So pause the video, give it a try, and then we'll continue. So I hope you gave it a good try. Let's go ahead and walk through this problem. So what's our decision variable? What do we have choice over? Well, we have choice similar to last time over how many of each product we make. And so I'll often abbreviate decision variables as DVs, and I'm going to write my decision variables as W and A, for W being the number of wood framed windows. And it's always good to note that the way the problem's set up, this is on a per day basis. And then the A variable will be the number of aluminum framed windows. Similarly per day. So I've got some of each, and I need to choose how many of each do I make. What's my goal? Well, my goal here is going to be to maximize total profit. Actually, in most of these homework problems or example problems, it will be pretty explicit about what it is that they want to minimize or maximize. What's their goal? And so in this case, we want to maximize profit. And so we want to maximize profit. And that profit is, well, our profit contribution from wood frame window is $300 of profit per window. So 300 times the number of windows that we make is the profit per day from windows. And then we get $150 of profit per window for our aluminum framed windows. So it looks like the wood frame windows are a little bit more desirable. They've got a higher profit margin on them, but doesn't mean we should just necessarily make only wood framed windows, because we've got some constraints. If we didn't have any constraints, then say, yes, make as many wood framed windows as you could, and don't make any aluminum framed windows. But we've got some constraints. So I'll bring my kind of constraints over here. Maybe I didn't leave quite enough room. But we've got 3 constraints, each of them having to do with our 3 employees and the labor that's available from each of them. So I'll write ST, it's abbreviation for subject to, that we want to maximize this, subject to some constraints. And so for the first constraint, we've got a limit on Jacob's labor. And Jacob is the person that makes the wood framed windows, and he can make 6 per day doing the framing. And so we get W is less than or equal to 6. We've got specialized labor here. Only Jacob makes wood framed windows, or at least does the framing. And so we can only make as many wood frame windows as he's able to make. Eva is our specialist for the aluminum framed windows, and she can make 4 of those. So maybe they're more time consuming to make, and so she can make 4 of them in a day. And then Noah contributes the glass. And so whereas these were number of windows that could be made for their constraint, this one, the units are going to be in square feet of glass. And apparently, whatever sheets of glass that he makes, he's able to make 48 square feet of glass. And so the total glass that's available is 48 square feet per day. And some of that is going to be taken up by the wood framed windows, 6 square feet per window. And so 6 times the number of wood framed windows gives us the square footage of glass used by the wood framed windows, and 8 square feet per aluminum framed windows. So the aluminum windows must be larger, which might be why Eva can only make 4 of them per day. So those are our 3 constraints in this case. And yeah, that's what's limiting us from just making an infinite number of wood framed windows and maximizing our profit that way. So drawing a picture of this, and we'll follow up in Desmos as well. I'm going to put wood framed on the x-axis, aluminum framed on the y-axis. Let's start off with our first constraint at 6. So let's do 6 wood framed windows there, and I'll do that one in blue. And we need to be less than or equal to 6, and so I'm going to put an arrow on that, pointing that we need to be the left of that line to fulfill Jacob's labor constraint. Then we'll do Eva's labor constraint. She can make up to 4 of the aluminum windows. And so let's do 4. That's going to be a horizontal line, and she needs to be below that line. And so our feasible region right now is this rectangle. And so if we only had their constraints, we'd sort of have a nice rectangle here, and we'd probably end up at this corner. But that corner is going to get cut off by the constraint from Noah's glass that's available, and that's a shared resource, and that's going to give us a diagonal line. And so plugging in, that will intercept down here at 8 and up here at 6. And so I'll draw that in as well as I can as a straight line, and we need to be below that line. So there's our constraint for Noah's glass, and we need to be below that. And so this region, sort of this weird rectangle with a corner cut off, is our feasible region. If we think about what direction our objective points in, if we draw a vector in the direction 300, 150, or just in that scale of 300 to 150, or kind of 2 to 1 ratio, 2 in the W direction, 1 in the aluminum direction, it's going to be a vector pointing that direction. And so we want to move as much in that direction as possible. So, and maybe here's our feasible region here. So I went ahead and used Desmos to fill in what are the corner points here. So I'll go ahead and label them. So this is 6, 1.5. Here we've got 6, 0. Here we've got 2.67, 4, or 8/3. And then here we've got 0, 4. And can't forget that we also have 0, 0. In most of these maximization problems, 0, 0 is never the actual choice, but it will be sort of a starting point for us later when we start talking about the simplex method. So those are all my corner points. Now that I've got my corner points, I can go ahead and set up and find out what is the objective value at each of those corner points. So feel free to use an online calculator like Desmos. Actually, you can use it to compute these objective values as well. And so here's my corner points or my CPs. 0, 0, 6, 0, 6, 1.5. I'll abbreviate this down to 2.7, comma 4, and then 0, comma 4. Okay, and then my objective function is going to be z equals 300 w plus 150 day. And I'm going to write out that objective function there because eventually we're going to change the objective function and I'm going to have extra columns for those modified objective functions. So for this original objective function, the origin, if I make no wood framed or aluminum framed windows, I make no profit. If I make 6 wood framed windows and 0 aluminum framed windows, my profit is 1,800. If I make 6 wood framed windows and 1.5 aluminum framed windows, how can we make 1.5? Well, maybe Eva makes 3 windows every 2 days. That you also then have to think about, well, now Eva's under or has less work than time. And so do you have another activity for Eva to do in that time? Or are you only hiring her for that portion of the day or a few days a week for her to make some of those aluminum windows? But if we look at that 6, 1.5, we get an objective value of 20, 25. At this corner point, we make 2 2/3 wood windows and 4 aluminum windows. That would be eight wood windows every 3 days. Here we get an objective value of 1,400 if I sort of use the full decimal value there. And then lastly, I could just make 4 aluminum windows and no wood windows, and that would give a profit of 600. Okay, looking at this then, our optimal solution is the one with the best objective value. In this case, this 2025 comes from this point here. That is the point that maximizes our profit. Okay, and so you'd have to do some arrangement with Eva of she's going to be underutilized and she's going to have some excess hours, and whether you reassign her to some other task. Ideally, if she could make glass too, it'd be worth retraining her. But yeah, there's many practical things to consider by kind of what's meant by some of these solutions. And actually, in a practical solution, there would be maybe our 2 variables are 2 products, and I often think of decision variables as activities, and right, one activity is to make that product, right? There's other activities that the business does, and so you might want to also include those as decision variables. And you could devote labor to those as well, and they might have some profit connected with those activities, or they might not have any profit connected to them, but they might need to be done in order to enable some of the other profit-bearing activities. And so in a practical one, you'd have more than 2 decision variables, and maybe Eva would be utilized by one of those other decision variables. So that's our optimal solution for the original problem. Now let's look at the modifications. This is sort of previewing what we'll talk about later on when we start talking about sensitivity analysis. In that we've sort of been given the values that we've used as really the coefficients in here, as well as the values on the right-hand side and the values that are coefficients in the constraints as well. But oftentimes those are best estimates and they might be subject to change. And so there's often some uncertainty in the values there. And so let's go ahead and let's play a little bit of what if and look at what happens if a new competitor moves into town who's now making wood framed windows. Wood framed was sort of our best profit margin product, but if we have to compete with somebody else, we're probably going to lower our price so that we don't then introduce a new constraint having to deal with demand on wood windows diminishing because somebody else is making wood windows. So if we reduce our profit margin, that's going to change our objective. And so let's look at a couple of alternate versions of the objective. Now let's look at what happens when we decrease it to 200 per wood window. And so now this is going to be 200 W plus, we're still going to get the same profit per aluminum window. Our competitor is only making those wood framed windows. Must be that they see that they're a hot commodity in our market. And once we change that, if you go ahead and compute the new updated objective values, you'll get 0, 1200, 1425, 1133, and 600. Okay. With this updated version, our optimal value is still to make 6 wood windows and 1.5 aluminum frame windows. And so the decision wasn't changed by that change in the objective value. Visually, our feasible region didn't change at all. What happened is that we actually got a little bit less profit from our wood windows. And so the arrow that points in the direction of increasing profit sort of moved a little bit more this direction. So it's not pointing as much towards this point, but still not pointing fully towards that point yet. Okay. Now let's go ahead and decrease it. And let's say we have to cut prices at such a point that we are only making $100 of profit now for our wood windows. And so now it's 100 W plus 150 A. And if we look at those updated objective values, we'll get values of 0, 600, 825, 867, and 600. So now if we reduce our profit margin enough on the wood windows, essentially our arrow will kind of shift more this way, and then we get a different optimal solution because we're getting less profit per window. We're now going to make less wood windows. We're going to make 2 2/3 wood windows and 4 aluminum windows. So now we're going to max out Eva's labor, and we're making all the aluminum windows we can, but we're now making fewer wood windows. And so Jacob will have to find something else to do with his time. So yeah, we can change our objective coefficients, and that will sort of change the arrow, the direction of this arrow, and that might involve then moving our new optimal value to being at this corner. Okay. Let's look at this last one. Jacob is considering lowering his working hours. Let's reset the objective to the original one. But he's reducing his working hours, making wood frames to only 5 wood frames per day. And so if we think of that, that would move this line over to 5 here. And so let's maybe draw that on here. What you'll notice is it cuts off this portion of the feasible region. So what was before a feasible solution, an optimal solution, is no longer a feasible solution. And so if it's not feasible, it can't be optimal. And so now we've got a new corner point here. We've also changed a corner point here. And so let's figure out what those new corner points are. The new corner point here ends up being 5, 2.25, and then we've got 5, 0 down here. So with those new corner points, let's check their objective values. And so here, I'll make some space down here, corner point. And my objective is Z equals 300 W plus 150 A, using that original objective. And at 5, 0, we get a objective value of 100 or 1500. And at 5, 2.25, we get an objective value of 1837.5. Okay. Comparing them with these other values, so we still have 0, 0, and we still have this solution is still a feasible solution, and this solution is still a feasible solution. This one ends up being our optimal solution. And so essentially our optimal solution moves from this corner, which is no longer feasible. Now it's at this corner here. So this was a pretty good example of how to set up your linear program, how to solve it graphically, and feel free to use Desmos to draw the picture as well as to compute the objective values. And then we did a little bit of what we'll call sensitivity analysis, looking at the what ifs of what happens as I change the various parameters of the problem.